Get started. So today we're going to be talking about open loop op amps. Before we get into that specifically, I want to talk a little bit about feedback in op amps. So we'll change this to black. Feedback configurations. Okay. So there are really only three options that we are going to see. The first of which is open loop amplifier circuits, which we'll be discussing today. And in an open loop amplifier circuit, you'll have something like this. This can be our non-inverting input terminal. This will be our inverting input terminal. This will be our output terminal. So let me label things here: V plus, V minus, V out. And then just because I want us to get used to seeing it, I'm also going to label our power supply terminals VCC plus and VCC minus. But these power supply terminals have literally nothing to do with feedback configuration whatsoever. So this representation that I have drawn here would be what's called an open loop circuit. It's an open loop circuit because there is no feedback path available. Okay. Then we're going to talk about positive feedback circuits, which will be our topic for Friday. So I'm going to redraw my amplifier really quickly. Plus, minus, here is our non-inverting input terminal. Here is our inverting input terminal. Here is our output terminal. We're going to have our supply voltages VCC plus and VCC minus. And then what makes this a positive feedback circuit is when we put an element that connects the non-inverting input terminal to the output terminal. I'm just going to put a generic circuit element here. For most of our applications, it will be a resistor, but it's possible for it to simply be something like a capacitor, inductor. I don't think you would really ever use a wire because that's just going to force your output voltage to be the same thing as your inverting input voltage, which is defeating the purpose of positive feedback, which we'll talk about in a little bit. But anyway, positive feedback circuits are characterized by connecting the output to the non-inverting input terminal through some conductive path. And then lastly, we have negative feedback circuits, which is effectively the exact same thing as a positive feedback circuit, except that our feedback path goes from the inverting input terminal to the non-inverting input terminal, excuse me, to the output terminal. So here's V plus, V minus, V out, supply voltage terminals VCC plus and VCC minus. And now we are going to have some component linking the inverting input terminal to the output terminal. And this is an example of a negative feedback circuit. Positive feedback circuits and negative feedback circuits have specific characteristics because of the application of feedback. And we're going to talk about those characteristics at least a little bit in this class when we cover those types of circuits, and we'll go into much greater detail when we start designing our own amplifiers in our electronics courses. So today we are going to be focusing on this open loop configuration. So with that description out of the way, now let's talk about open loop op-amp circuits. So the circuit that we analyzed at the end of our last class meeting was an open loop op-amp circuit because it did not contain any feedback path. One of the things that we noticed about that open loop op-amp circuit was that it had a very, very small linear range that depended on the open loop gain of the system as well as the supply voltages. So just to recap things really quickly, if we have an open loop configuration like so, here's our positive, or excuse me, our non-inverting input terminal. Here's our inverting input terminal. I'm going to do this in green so that we can see it. This is our differential input voltage VD, always measured positive polarity with respect, or excuse me, non-inverting input with respect to inverting input. Here is our output voltage. Then we had our supply voltage here. And here we found that our linear range for such a system extended from VCC minus over the open loop gain of the amplifier was less than our differential voltage, was less than the positive supply voltage divided by that same open loop gain. So when AVOL is very large, which is true for most op amps, this linear range is incredibly small, which means that there is a very small range of input voltages that can actually be amplified. So the output is just a scaled version of the input. In all other cases, we find that our output voltage saturates to either the positive supply rail or the negative supply rail. So in an open loop configuration, typically speaking, we use the amplifier in this saturation mode, okay? So we're trying to get the amplifier to saturate because it's the amplifier itself is practically unusable as a linear amplifier because of how large the voltage gain is. So let's talk about how we can use this saturation to our benefit. So the first circuit that we are going to look at is what's called a non-inverting comparator. So in a non-inverting comparator, we have our op amp, with our non-inverting input terminal and our inverting input terminal. Here is our output terminal. Here's our positive supply voltage, VCC plus, and down here is our negative supply voltage, VCC minus. And typically speaking, let me do these in green, we are going to apply an input voltage to the non-inverting input terminal, and we will apply some reference voltage to the inverting input terminal. So let's play around with an op-amp circuit like this, with this configuration that actually has some numbers. So let's say that our reference voltage is 2 volts. Let's say that VCC plus is equal to 10 volts and VCC minus is equal to negative 10 volts. And then I'm also going to specify our op-amp parameters. So let's say that our open loop gain is once again 100,000, so 10 to the 5 volts per volt. Our input resistance Rn will be on the order of 1 mega ohm, and our output resistance will be on the order of, let's say, 10 ohms. The value of this, as we'll find out in a moment, isn't exactly going to make any difference. So I'm going to draw the practical circuit model for this circuit, or using the practical op-amp model. And that's what we're going to use to analyze this thing until we get a little bit more comfortable with these guys. So I'm going to start by drawing the op-amp itself. So here's my non-inverting input terminal. Here's my input resistance of 1 mega ohm. Here's my inverting input terminal. And I'm going to define my differential voltage VD here. I'm going to have 10 to the 5 times VD here. My output resistance of 10 ohms will go here. Now I'm going to make my external connections, right? So my output voltage, like there's nothing connected to the output terminal. So my output voltage is just the voltage drop seen at that terminal with respect to ground. Between my inverting input pin and ground, I have my reference voltage, which is 2 volts. So I'm going to put a 2 volt source here. And then between my non-inverting input terminal and ground, I have my input voltage. So, and I'm just going to call this voltage Vin, and we're going to play around with it a moment. What we should be able to see here pretty easily is that our output voltage V out for this particular system is going to be 10 to the 5 times our differential voltage VD. Our differential voltage VD is just Vn minus 2 volts. And so if we substitute this relationship in, we're going to have 10 to the 5 times Vn minus 2 volts as our output voltage. Okay. So if we plotted the output voltage versus input voltage for this circuit, we'll have something like this. Like this is going to be my graph. So let's see, this will be V out measured in volts, Vn measured in volts. We put some hash marks here, 2, 3, 4, 5. 1, 2, 3, 4, and 5. So this will be, so excuse me, -5, -4, -3, -2, -1, and 1, 2, 3, 4, and 5. And then on the vertical scale, I'm only going to put a single hash mark. This is going to be for VCC plus, which is 10 volts, and down here is going to be for VCC minus, which is -10. So I'm going to move this graph over just a smidge so that I can also make a little bit of a table here. And it's going to help us fill out our graph. So I'm going to put VN in one column, V out nominal in one column, and then V out actual in the last column. So let's start by looking at a very negative input voltage. So let's start with VN is equal to -5 volts. If we plug VN is equal to -5 volts into our expression for V out here, we're going to have 10 to the 5 times -7 volts, which seems like it should be -700,000 volts, because the output voltage of our op amp cannot be more negative than the negative supply voltage. We are in saturation, and so our actual output voltage is -10 volts. So I'm going to put a little dot right here. Now let's move on. Because I know how this circuit works, I'm going to jump a few voltages ahead. Let's look at what happens at 0 volts. So at 0 volts, we're going to have 10 to the 5 times -2 volts. Looks like -200,000 volts. Excuse me, I need to put another 0 there. Which once again is more negative than our negative supply voltage. So this is still going to saturate to -10 volts. And so it should be fairly easy to understand that for all voltages between 0 and -5, we're going to hit saturation. And so I can draw this line like so without losing any information. Let's look at .99 volts as an input voltage, right? So that means our output is going to be 10 to the 5th power times 1.99 minus 2, which comes out to be -1000 volts, which is more negative than VCC minus. So this is still going to look like -10. So at this point, just before 2, we're still at -10 volts. If we look at 2.01 volts, a point just on the other side of 2, our reference voltage, we're going to wind up having positive 1000 volts, which means we'll saturate to +10 volts. So just on the other side of 2, we'll have a point here. And then for the sake of argument, let's look at +5 volts. So that's going to be 10 to the 5 times 3 volts is 300,000. which is greater than VCC plus, so we saturate positive 10. So I'm going to connect these dots, making through to pass through 0 like so. And this is what our response or our output versus input voltage relationship looks like for a non-inverting comparator, okay? So from this numerical example, we can actually draw some general idea of how this circuit behaves. So for a non-inverting comparator, we will see that our output voltage is equal to our positive supply voltage whenever our input signal is greater than our reference voltage, and our output voltage will be equal to our negative supply voltage whenever Vn is less than our reference voltage. It's only when our input voltage is extremely close to the reference voltage, within a few microvolts to millivolts, that we will actually have linear amplification. But for the overwhelming majority of the range of input voltages, we are going to be at either positive saturation or negative saturation. So this circuit is called a comparator because it simply compares the input voltage to the reference voltage, and then either the output is either high if the input voltage is greater than the reference voltage, or the output is low if the input voltage is less than the reference voltage. So this is how we are using the very small linear range of an open loop op-amp configuration for a practical purpose. We're able to compare the strength of our signal to some reference voltage value and see whether or not we have exceeded that voltage or a reference voltage or not. So a secondary circuit that we're going to look at is the inverting comparator. And the inverting comparator is effectively the exact same thing as a non-inverting comparator, except that we swap the position of the input signal and the reference signal. So when this inverted comparator, let me scroll up here. Right. Here is our non-inverting input node, our inverting input node, our output node, positive supply voltage, negative supply voltage, here is where we're going to apply our reference voltage. Here is where we're going to apply our input voltage. And what we should see using the same values as before. So let's call our reference voltage 2 volts, VCC plus as 10, VCC minus as negative 10 volts. The only thing that has changed is effectively what our definition of VD is, right? So VD now is going to be 2 volts minus VN instead of VN minus 2 volts. So it is exactly negative what our previous VD was. So using that information, we can really just jump straight to the behavior of this thing without having to go through all of the work of building a table and all that kind of good stuff. So here's V out. Here's V in. I'm just going to make one notch here for 2 volts for our reference. This is positive 10 volts. Down here is negative 10 volts. And what we're going to see in the inverting comparator is the exact opposite response. So our output is going to be high until we hit our reference voltage. Then it's going to fall low. And once again, this is because the input voltage and the reference voltage have simply switched positions. So for this inverting comparator, our output can be described as VCC plus when Vn is less than V reference, and VCC minus when Vn is greater than V reference. So typically what I do now, at least when we have a live class meeting, is I would give the students a simple design problem to work. But since there's only one student online and I don't want to put them on Front Street to have to answer everything, I will just talk our way through this design problem. So what we are going to do here is we are going to use our knowledge of comparator circuits to design a 1-bit analog to digital converter. Commonly called an ADC. And here are our design constraints. We want V out to equal 5 volts when V in is greater than 3 volts, and we want V out to equal 0 volts when V in is less than 3 volts, okay? So because we are comparing our input signal to a single specific reference voltage, this tells us that we need to be using a comparator, okay? So I'm going to start by drawing my open loop op-amp circuit. Like so. So what we are going to be choosing here is effectively what our reference voltage is and where to apply it, where our input signal is applied, and what our supply voltages need to be in order to get the response that we're looking for, right? So in both cases, we are comparing our input signal to a constant value of 3 volts, which means 3 volts should be our reference voltage. So this begs the question of, are we using a non-inverting comparator or an inverting comparator? Since we want the output to be high or a large value when Vn is greater than 3 volts, that to me tells us that we're using a non-inverting comparator. And in a non-inverting comparator, I apply my reference voltage to the inverting input terminal, and I apply my input signal to the non-inverting input terminal. Now for my supply voltages, this is what my output voltage is going to saturate to. So when Vn is greater than 3 volts, we want our output to go high at 5 volts, which means we need a 5-volt supply voltage here. And when Vn is less than 3 volts, we want our output to be low at 0 volts, which means we're going to ground our VCC minus terminal. So the response that we should expect from this configuration is as follows. So here, excuse me, this should be V out. This is going to be Vn. Let's put 3 right here. And let's put 5 right here. And what we should see is our output voltage is 0 until we hit 3, and then it will jump up to 5. Okay. So what I'm going to do now is something that I regularly ask you guys to do whenever we do a design problem. We are going to simulate this circuit to make sure that it behaves in the way that we expect. So give me just a moment. I'm going to get my keyboard and everything set up, and then we're going to get into LT Spice. All right, so I already had LT Spice open, so I'm going to go ahead and start constructing my circuit here. So I already have a new schematic window open, so the first thing that I'm going to put in is my op amp. There are a whole bunch of different op amps that we can use. If we click on this op amp menu, we literally have hundreds, if not thousands of them to choose from. For the purposes of this class, we are always going to use Universal Op Amp 2. The reason why we're using Universal Op Amp 2 is because it has an editable slew rate limit, which we're not really going to use, output voltage and current limit, things like that. So effectively, this is going to be almost an ideal op amp, except that we can change the open loop gain, the input resistance, and the output resistance to specific parameters if we need them. And also, it is going to require us to connect external power in order for it to behave properly, which is one of the things that we're dealing with here. So we need power in order to set the output voltage constraints on our system. So I've got my Universal Op Amp 2 here, and I'm just going to drop it here in the middle and leave it alone. One thing that I want to point out, for this particular model, the non-inverting input terminal is on bottom, the inverting input terminal is on top, which is opposite to what I have drawn. The positive supply voltage terminal is on top, and the negative supply voltage terminal is on bottom, which is the same as what I have drawn. So when you're simulating these circuits using LT Spice, you do need to pay attention and make sure that things are connected correctly. Okay. So for right now, I'm going to leave this op amp alone, and I'm just going to move my screen over here, and I'm going to put up some voltage sources. I could connect my voltage sources directly to my op amp circuit, but I find that it makes things messy and complicated. So I'm just going to show you how I do things. You don't necessarily need to do it this way, but it does make things look a little bit cleaner. So the first thing that I'm going to do is I'm going to establish my supply voltages. So I'm going to have one voltage source on top here, and then I'm going to put another voltage source below it. And I'm going to tie these two voltage sources together. And I'm going to choose the center node as ground. So the reason why I configure my supply voltage like this is because this is physically how I would configure my supply voltages in a lab setting. And for those of you that had me for circuits 1, when we did our op-amp labs, this is exactly what we were doing when we were trying to power our op-amp. We had access to 2 positive 9-volt sources. We effectively wired them in series to give us 18 volts, and then we chose the middle node to be ground, so that from the perspective of that ground, we had plus 9 volts and minus 9 volts to apply to our different supply terminals. Okay. So for the circuit that we are dealing with, our positive supply voltage was 5 volts, and our negative supply voltage was 0. And what I'm going to do is I'm going to label these nodes VCC plus here, and then I'm going to put that same label on the positive supply terminal of my op-amp. And so what that does is it says, well, whatever voltage is at this node VCC plus is applied at this terminal of the op-amp, so that I'm going to put 5 volts there without having to actually have a 5-volt source connected to that node. Once again, it's just for the sake of making it look a little cleaner. Similarly, I am going to label that bottommost power supply node VCC minus, and I'm going to place that VCC minus label here at the negative supply voltage terminal. So now my op-amp is powered. I'm going to give myself some stubs of wire to use here to connect things to, just for the sake of making things look nice. For my reference voltage, I'm going to use another DC voltage source. So I'm just going to put one here. I'm going to ground the bottommost terminal. My reference voltage was 3 volts. So I'm going to make this a 3-volt source. And I'm going to label this as VREF. My reference voltage is applied to the inverting input terminal. So here. And now I am going to set up one final voltage source for my input voltage, grounding the bottommost terminal. So for this one, we need to choose a range of voltages. So just for argument's sake, I'm going to let my voltage range from -5 volts to +5 volts. And the easiest way for me to do that is to use a sinusoid. I'm going to give it a DC offset of 2.5 volts, an amplitude of 2.5 volts, a frequency of 1, and I'm just going to have it run for 1 cycle. The number of cycles that it runs for isn't particularly important. We can have it run in perpetuity, but I'm just going to have it run for 1 cycle in this particular case. All the other parameters I'm going to leave blank. I'm going to call this voltage source Vin, and I'm going to apply that input voltage at that node. And then lastly, just to make things easy to find, I'm going to label this output voltage node as Vout. Okay. So I have my non-inverting comparator circuit over here on the right, and then I've established all of the voltage sources that I'm going to use over here on the left to make this circuit as clean as possible. Now I'm going to simulate the circuit. So if I click the simulate button, I'm going to edit my simulation command, and I'm going to tell it to stop after, let's say, 3 seconds, although it really shouldn't matter, because we're going to not wind up not using that time thing in a moment here anyway. So this .tran3 thing that just popped up is telling the simulation software to run a transient analysis for 3 seconds. Now I'm going to press the running man icon, And for whatever reason, it's populated with some stuff from another thing that I did a while back. That seems weird. Let me try this again. Maybe I just didn't have it closed out. Nope, it's still doing it. That's very odd. Delete this pane. Delete this trace. Okay. So what I was expecting was a blank graph. I've now made my graph blank. Not entirely sure what was going on there, but we'll figure things out. So one thing that I want to look at here is my input voltage. So just, I'm going to click with this probe, this voltage probe where it says VN, and I can see that I have one sinusoidal cycle. Maximum value is 5 volts. The minimum value is 0 volts. So that's the, actually, I thought I wanted it from +5 to -5. So let me go edit this. If I want +5 to -5, I would do 0 DC offset and a 5-volt amplitude. Sorry about that. Let me rerun this. And now it's going from 0 up to +5, down to -5, and back to 0. So sorry for that mistake. Now I'm going to click on my output voltage. And what we can see, it looks like here, is that whenever our input voltage gets greater than 3, our output goes high. And whenever our input voltage goes less than 3, our output voltage goes low. There's actually a slightly better way to look at this graph. So what I have right now is V out and Vin plotted as a function of time. But the graphs that we developed for understanding how these works are V out as a function of Vn. So I can make LT Spice do that by moving my mouse down to the bottom here so that I'm looking at the horizontal axis. When I right click, I can change the quantity that I'm plotting with respect to. So instead of plotting with respect to time, I'm going to plot with respect to the voltage at node Vn, which is what my input voltage is. And now I have this graph. So I have this green line, which effectively has a slope of 1 because that's Vn versus Vn. I'm going to delete the green line because it's not really doing anything for me. And what I am left with is pretty much exactly the graph that I drew for how I anticipated this circuit would behave. For voltages less than 3 volts, we are at 0 volts. Once we hit 3 volts, our output swings up to +5 volts, and then it stays there at +5 volts. So this graph and this graph are effectively the exact same thing. So I must have designed my circuit correctly. All right, so one of the last things that I want to talk about here is an extension of this design problem. Give me just a second to reconfigure my computer. So in our simulation that we just did, we implemented this 3-volt reference voltage with an actual voltage source. Now, 5 volts is a very commonly used voltage in electronic circuits. It's the standard voltage that's output by USB ports. For those of you that did a lot of work with your Arduinos in your freshman series, you'll know that you were able to output a digital high of 5 volts using simple commands and things like that for your Arduino board. So 5 volts, very, very standard voltage. 3 volts is much less so. So if we don't want to use 2 different programmable power supplies, we could implement that 3-volt reference voltage by using a voltage divider network. So what I am suggesting is something like this. We're going to have positive supply rail set at 5 volts. I'm going to put my op amp here. I'm going to tie my positive supply voltage to that rail up top. I'm also going to have a negative supply rail down here at the bottom, which will be at 0 volts. So I'm simply going to tie this thing to ground. My input voltage is a variable voltage, so I'm not going to be able to use that with DC voltages. So I'm just going to put V in here. And then for my reference voltage, what I'm going to do is I'm going to bring it out here, and I'm going to use a voltage divider. So I'm going to put one resistor here, and one resistor here, so that there's a total of 5 volts drop across these two resistors. Now, since we're using a voltage divider circuit, just to refresh you guys' memory, this is what we're doing. Let's call this guy R1, this guy R2. Our reference voltage is just going to be VCC plus multiplied by R2 over R1 plus R2 in this case. So we are trying to get our reference voltage to be 3 volts. We know that VCC plus is 5, and so now we need to choose a value for R1 and R2 such that R2 divided by R1 plus R2 is 3/5. So to me, I'm going to do this the laziest way possible, and I'm going to put a 3 here and then a 2 here, so that R2 is 3 and R1 plus R2 is 5, so that my ratio is 3/5. Now, let's talk a little bit about the practicality of this. Okay. So generally speaking, when we are biasing an op amp, which is exactly what we're doing here by establishing this resistor network to supply a specific voltage to one of the pins, we don't want to use single-digit ohm resistors, nor do we want to use extremely large resistors, okay? So the reason for this is, since our output resistance is usually on the order of single-digit ohms, we want our biasing resistors to be much larger than that output resistance. And similarly, since our input resistance is on the order of mega ohms, we want our biasing resistance to be much smaller than that input resistance. So generally speaking, the sweet spot for biasing an op amp is to use kilo-ohm size resistors, because they're about 1,000 times larger than the output resistance, while being about 1,000 times smaller than the input resistance. So I'm going to make this guy a 2 kilo-ohm resistor, and this guy a 3 kilo-ohm resistor. And my expectation is that now I should see about 3 volts at this node by using this voltage divider network. So let's simulate this and see what happens. So what I'm going to do here is I'm going to make a new circuit. I'm going to leave all of that stuff alone for the most part. I'm going to reuse some of the things. I'm going to make a new op amp circuit that's just the thing that we just designed. Here's universal op amp 2. Let's put it over here. I'm going to give myself a long stub of wire like so. That's going to be my positive supply rail. I'm going to give myself another long stub of wire like so. That's going to be my negative supply rail. So I'm going to go ahead and wire my positive supply up to the top and my negative supply down to the bottom. I'm going to put the label VCC plus here. So now this rail is at 5 volts. I'm going to put VCC minus. Oh, I don't think the capitalization matters, but I'd like to be consistent. VCC minus down here. So that's going to be at 0 volts. I apply my reference voltage to the inverting input node. So I'm going to move that stub of wire out there, and I'll set up those resistors in a moment. My input is applied here. So let's do VN. I'm going to call this output node Vout 2, and I need to do that because the system will get confused if I have two nodes labeled as Vout, because that's where we're measuring at. And now I'm going to put my resistors in, right? So I'm going to have a resistor here and a resistor here, and let me just wire them up. I believe this guy should be a 2 kilo ohm resistor, and this guy should be a 3 kilo ohm resistor. Now, when I run my simulation, again, I'm not sure why that old information is saved on this graph. So let me just get rid of that. If I click my input node, I'm going to click my output node here. So that's the output node for the first circuit. And then this is the output for the second circuit. And notice that the red curve completely overlapped the blue curve, which means it's providing the exact same functionality, but it only utilizes a single supply voltage. So that 5 volts up here, this is ground, and we're using this resistive divider network in order to establish our reference voltage. So it's a little bit more complicated to set up, but it actually requires less equipment, which is generally speaking a good thing. All right, I think, oh, actually, let's look at one thing really quickly here. So I'm going to mouse over, actually, I'm not going to mouse over. I'm going to delete all these traces really quickly, because what I want to look at is the current flowing into the op amps nodes. Add traces. So let's see. Let's just look, for the sake of argument, at the current flowing into the inverting input terminal of our second op amp. So that's going to be this guy right here. Right. Tells us that it's effectively 0 milliamps, right? But what if, I'm not sure what's going to happen here, so let me be clear, I might be disappointed. I change this resistance to 2 mega ohms and this resistance to 3 mega ohms. Still looks like it's 0. I was expecting to see some small amount of current. Let me play with something really quickly here. Actually, let me just look at this thing. Okay, so the input resistance here is set as 500 mega ohms. All right. So let's make this 200 and this guy 300 and see if this has any effect. What I'm expecting to see is that if we have our input resistances set too large, the op amp is going to start leaching current effectively. Still looks like it's 0. But if we mouse over this node, we can see that the DC operating point is now 2.9 volts instead of 3. Whereas when we bring this down to 2 kilo ohms and 3 kilo ohms, this node is at 2.99999 and some change, right? So the larger we make those resistors, the more we're going to see this reference voltage point drift away from what we were trying to set it as. That's the point that I was trying to illustrate, but the current wasn't working out for me. The voltages are looking good though. All right, I think that is enough out of me for today. So unless anybody has any questions, I will see you guys on Friday, where we're going to talk about positive feedback op amp circuits.